กราบเรียนท่านประธานแล้วก็ผู้เข้าร่วมอบรมสัมมนาทุกท่านนะครับขอต้อนรับเข้าสู่ช่วงบ่ายเซสชันสุดท้ายของงานสัมมนาคอนเฟอเรนซ์วันนี้นะครับซึ่งก็ได้แก่เซสชันของ Tunneling นะครับ สำหรับเซสชันนี้จะมีวิทยากรทั้งหมด4ท่านนะครับประกอบไปด้วยดร. Harald Wagner นะครับคุณกิติเอกวรลบนะครับจากทางรฟม.นะฮะดร.โสภัทร วรวิวัฒน์แล้วก็คุณชินวุฒิชาญฉายาจากทางช.การช่างนะครับและท่านสุดท้ายคุณสุวัฒน์ศรีวงศ์นะครับจากทางบริษัทวิศวกรรมธรณีและฐานรากนะครับจะมาบรรยายในเรื่องของอุโมงค์นะครับโดยเฉพาะอุโมงค์ในเขตกรุงเทพมหานครซึ่งก็คืออุโมงค์รถไฟฟ้านะครับที่กำลังดำเนินงานก่อสร้างกันอยู่นะครับแล้วก็จะมาดูว่าต่างประเทศนะฮะจะมีการพัฒนาโครงข่ายอย่างไรบ้างและในเมืองไทยเรามันจะมีโครงข่ายรถไฟฟ้าต่อไปในอนาคตนี่ยังไงนะครับแล้วก็จากนั้นเนี่ยทางช.การช่างก็จะมาบรรยายเกี่ยวกับเรื่องของเทคนิคการขุดเจาะอุโมงค์โดยใช้ชิลทันเนลลิ่งนะครับที่กำลังก่อสร้างกันอยู่นะครับแล้วก็สุดท้ายทางคุณสุวัฒน์ก็จะมาบรรยายเกี่ยวกับเรื่องความปลอดภัยนะครับการติดตั้งอินสตรูเมนต์การตรวจวัดนะครับเพื่อความปลอดภัยในระหว่างการก่อสร้างแล้วก็ในระหว่างที่โอเปเรตด้วยนะครับในโอกาสนี้นะครับขอเรียนเชิญวิทยากรท่านแรกนะครับดร. Harald Wagner นะครับซึ่งท่านปัจจุบันเนี่ยทำงานอยู่ที่บริษัท DHW นะครับตำแหน่งก็คือ Consulting Engineer นะครับประสบการณ์ของท่านเนี่ยมีมากกว่า40ปีนะครับในสาขาทางด้าน Tunneling นะครับงานที่ท่านทำมาเนี่ยนะฮะเยอะมากมายนะครับก็มีงานออกแบบทางด้านอุโมงค์นะครับที่ปรึกษาแล้วก็ควบคุมงานก่อสร้างนะครับนอกจากนี้ปัจจุบันท่านก็เป็นทางผู้เชี่ยวชาญอิสระด้วยนะครับก็ให้คำปรึกษากับหลายบริษัทสำคัญในทั่วประเทศแล้วก็ทั่วโลกด้วยนะฮะในอดีตท่านเคยดำรงตำแหน่งเป็นรองศาสตราจารย์นะครับของมหาลัยที่ออสเตรียนะครับ Technical University Graz นะครับและท่านยังเคยดำรงตำแหน่งเป็น Vice President ของ ITA ซึ่งก็คือ International Tunneling and Underground Space Association นะครับซึ่งก็เป็นองค์กรอันดับต้นๆนะครับที่เกี่ยวกับทางด้านงานขุดใต้ดินแล้วก็อุโมงค์นะครับประสบการณ์40ปีของท่านเนี่ยนะฮะก็ไปทั่วโลกเลยนะครับไม่ว่าจะเป็นเยอรมันนะครับอเมริกาตุรกีนะครับแล้วก็ประเทศจีนแล้วก็อีกหลายประเทศที่ไม่ได้กล่าวถึงนะครับซึ่งในปัจจุบันนี้ท่านก็ได้ให้เกียรตินะครับมาช่วยงานในเขตของเมืองไทยของเรานะครับซึ่งโครงการที่ท่านได้เกี่ยวข้องอยู่ในปัจจุบันนี้ก็เป็นทางด้านรถไฟฟ้าสายสีน้ำเงินส่วนต่อขยายนะครับรถไฟฟ้าสายสีม่วงนะครับแล้วก็มีรถไฟรางคู่มาบกระเบานะครับนอกจากนั้นท่านก็ยังเดินทางไปสิงคโปร์บ้างนะครับไปที่อินเดียบ้างไปมีหลายโครงการนะครับโดยเฉพาะที่อินเดียก็จะเป็นอุโมงค์ที่เกี่ยวข้องกับทางด้านไฮโดรพาวเวอร์นะครับก็จากประสบการณ์ที่ท่านมีทั้งหมดเนี่ยก็ถือเป็นเกียรติอย่างสูงนะครับที่ท่านได้ให้เกียรติมาบรรยายในเซสชันของ Tunneling ในวันนี้นะครับขอเรียนทุกท่านยินดีต้อนรับกับดร. Wagner ด้วยครับ Please welcome Dr. Wagner.
First of all, I would like to thank the Thai Geotechnical Society for the invitation to make a presentation today to you. The title of the presentation is Tunnels for a Global Urban Sustainability, and there's a subtitle which has to do with costs and benefit with this type of underground urban constructions. Okay. This slide shows you the content, and basically I would like to focus in the next 30 minutes on the urban sustainability through underground construction for mass transport. So I will give you an overview of the development of the so-called evolution of metro stations, because metro stations are a very good indicator for the sustainable development of a city. And if time allows, I would also like to give you some ideas of how on a global basis, underground construction contributes to the global development of today. So urban tunneling is a challenge. It's a multiple challenge actually, for both for the owners, it's a challenge for designers, it's a challenge for contractors. And why is it a challenge? The challenge comes from the uncertainty, from the heterogeneity or inhomogeneous ground phenomena which we encounter when we do underground construction. It's also a challenge from the point of view of the difficulty to predict groundwater levels and groundwater influences, and also a challenge in regard to the impact of long-term and sustainable planning and construction works. Tunnel is something which is design and construction. Basically, we do construction through design. First of all, we make the design, but when we have done the design, we do the construction through the design. It is strongly influenced by investigation of ground conditions. It is influenced by the improvement which we want to achieve through the encountered inhomogeneity of soil or of rock mass, and it results in highly difficult construction scheduling. Construction schedules are developed at the beginning of a project, and at the end of the project we have the result from the challenges which we had to face in regard whether we can stay within schedule or not. There are problems in design and construction because we have to make a determination of the hazard scenarios during design and during construction. How do we do that? We do that through risk management, through risk assessment, risk mitigation, risk management in construction. We also have to understand rock mechanics and soil mechanics, and we have to develop respective models and failure mechanisms. We also have to develop structural measures for a risk mitigation strategy, and we always have to make the best economic solution, the best cost-benefit solution. We are in an increasing urbanizing and an increasing populated world. The global population is facing rapid changes with a constant migration towards the cities. That means that the rural population is decreasing, the urban population is increasing. So we have population growth. We have also environmental risks because we want to serve our population, and we have to take into account the risks from the environment when we do this. And we also have a limitation of resources. We need resources to provide to the population, but there is a limitation of resources. For instance, the natural gas and natural oil resources in between 30 and 50 years will be finished. What is the sustainable urban development? The urbanization starts, and from my point of view and from the point of view of this presentation, with metro stations which are, if we do it in a cut and cover way, environmentally harmful. Urbanized cities, they have a tendency to show that through the implementation of underground structures, and in particular underground stations, there is an indicator that we are urbanizing. So the sustainable urban development starts, we want to have a resilient city and a safe and healthy city also. We want to have our city to be a planned city, and we want to also have a productive city. Means that we have to offer jobs to our people. We have to have an all-inclusive city that serves to the population, and above all, we want to have a green city. So why are city planners attracted by mined metro stations? First of all, they leave the surface untouched. Life on surface is going on. They use mining methods in order to provide the untouched surface and create space for entering into and for exiting out of mass rapid trains. So city planners are challenged by underground works, in particular if there is shallow overburden, which in general is the case. We don't want to go very deep with our underground structures. We want to be near to the surface. It is difficult, considered, the ground is considered to be difficult, and most of the people think that it is expensive. It is expensive if we just look at the construction cost, how much is the concrete, how much is the cost for the reinforcement and so on. But this is not enough. We have to look into life cycle cost. And mined underground structures are more difficult to understand than cut and cover structures. If we have a cut and cover structure, okay, we make a trench into the ground and we put the box into that trench and then we cover it again. This is very easy to understand. When it comes to a mined underground structure, then we have to give an answer, a simple answer to the question of how can we face with geotechnical problems, how can we face with hydrological problems. We dig underground and then people are afraid that some of the buildings above may get damages and this, to explain how we control this risk, is not easy. Now, metro stations have had a so-called evolution. It's an evolution like in other natural phenomena also. First of all, it is attracted by virtually unlimited availability of space and unlimited configuration possibilities through an underground station. We can, and in the evolution I will show you that we started with metro station sections of 120 square meters, and now we are far beyond 200 square meters in much, much more difficult ground. Second, the capability to minimize settlements means minimize surface displacements of the surrounding ground. We have gained so much experience over the past decades that we can that we have developed this capability and we can control settlements. And third of all, we should be confident about the technology, how to monitor and how to control displacement with calculated predictions. In the designer who makes a design for a metro station will make a calculation of the settlements, and now we have to convince the public, the client, our colleagues in a team that we are able to control the settlements, the deformations, displacements through monitoring. Now I'm talking about conventional station design mainly because this is the most popular type of station design. Conventional, why? Because it is using so-called conventional tunneling methods, CTM. In Asia, CTM is also named NATM, means New Austrian Tunneling Method, because it started with the use of the geotechnical understanding, with the geotechnical philosophy of the New Austrian Tunneling Method, but it has not been developed first in Austria, but in Germany. It started from Germany. So there are specific advantages for the conventional mining of station design, in particular when we are close to sensitive and valuable historical structures. We know that through every excavation we do underground in the mining method, we are causing a shift of stresses in the underground. And we know how to limit the shift of stresses in the underground in order to keep the integrity of the ground as much as possible to its original geotechnical properties. We can optimize station configurations after evaluation of sustainable design alternatives. Usually we do not do only one design alternative, we do several design alternatives and then make an evaluation and choose the best one. Now there was a design evolution of stations in the first phase between 1974 and 1995, about 20 years. And this slide shows you the list of station designs which have been starting in Germany and finally went through a number of countries, including Mexico and Italy and United States and also France. So this is the first phase of station evolution. Each of these stations provided experience which is available for future use. And the second started about 1992 until 2006. So it's about 15 years. This second phase of station evolution in different countries, including Hungary, also where Thailand has been so successful to get the award for the World Tunnel Congress in 2012. Now actually it started with this 120 square meter excavation cross section in Bochum in Germany. Bochum is a small city, it has about 250,000 inhabitants. However, the traffic congestions in this city was such that the people said, well, we are a small city, we have to use our surface if we want, if we do a metro and a metro station, we want to do it underground. And that's how it happened. You can, oh, sorry. Okay. You can see that this is the first excavation tube, station platform tube, and this is the second station platform tube. Here you can see these in construction. So when the second station tube was placed on top of the first one, of course there was some pillars in between the two which gave support to the station, because we have to manage the flow of forces in the underground. The next one was another metro station for the subway of Nuremberg with separated platform tunnels, but the separated platform tunnels have been connected with access tunnels from one platform to the other platform. It was about the same size of the 120 square meter for both platform tunnels together, but instead of the structural concrete pillar in between, there was a earth pillar. You can see here the earth pillar, which of course needs some geotechnical consideration because of the forces coming down here and have to be guided around here. So this pillar, earth pillar in between, is getting a higher stress and has more stress accumulated than before. Now this is a so-called multiple drift station in Munich, which was first time 185 square meter, so big step forward from 120 to 180 square meters. And this was, I call it an export product hit, because this type of station has been used in many other countries to follow the first time of the Munich so-called Theresienwiese station. Those of you who like to drink beer, they know that in October, under this area, under this surface, there is a station, but on top there is a lot of beer drinking. It's a famous Oktoberfest in Munich. So in North America, the Fort Totten metro station for the Washington metro did follow almost exactly the same structural principles as it has been experienced for the Munich metro, with one additional aspect, and this is the environmental aspect, because this Fort Totten station has been constructed underneath a park. And there was a competing between cut and cover to do the station in cut and cover and the station in a conventional mining method. And the conventional mining method has been cheaper, just comparing the construction cost, the cost for the civil works, but it saved 10,000 trees on top of that station. So for the people from Washington, capital of the United States, it has been very important to save the park and to save the trees where they do their jogging and so on. So it has an environmental aspect which has not been reflected in the cost, though the cost of the mining method has been cheaper than the cut and cover. So it was a big success. Now this slide just shows you the excavation steps, and just briefly, there's a central gallery here, and the central gallery is excavated in excavation steps 1, 2, 3, and then the bottom beam is installed, and then the pillar is installed, and then the roof beam is installed, and then the sidewall galleries here and here are excavated, and finally these shotcrete shells in the profile are demolished to get the full station size. Washington Metro, of course, all these needs state-of-the-art of numerical modeling. Today we finite elements, and this shows you in a more detailed start of the central gallery with a top drift, and then the central gallery full excavation, installation of bottom beam, pillars, and roof beam. Finally, the sidewall galleries, and then demolishing the sidewall galleries and get the full cross section plus the installation of the platform. Some slides from the construction. This is the portal wall, and you can see the central gallery. You can see the sidewall gallery here, and the sidewall gallery on this side. The central gallery already started to have the beams. Another side drift excavation, more detailed picture from the side drift excavation. And the next shows you that this all has been in real soft ground. So some pre-running support, umbrella-like support had to be installed. Also, you can see conventional tunneling using mostly in Europe nowadays lattice girders, so they are not full profile steel arches. Lattice girder give a better compound for the shotcrete. The shaft construction also has been using first time shotcrete technology or new Austrian tunneling method. So the shaft, it was a 25-meter diameter shaft, was excavated from the top to the bottom using shotcrete. Here you can see this is the shaft, and then from the shaft there is a break out for the so-called ventilation tunnel beyond the station. For the Los Angeles Metro Red Line, we have designed the first time a hybrid solution, which is a TBM tunnel here in this cross section and a TBM tunnel here, and a mined central gallery following the same principle as for the Washington and Munich Metro, with the bottom beam, the pillar, and the roof beam, where particular emphasis has to be given to the connection, which is in every multiple drift structure using conventional tunneling method, shotcrete method. You have to pay specific attention in your design and then with the design in construction for the connections. For the Chabri Bazaar station for metro in New Delhi in India, special design has been developed with the access to the station here from these cut and cover shaft areas, and then the platform tunnels, mining sections for the platform tunnel with connection galleries in between the platform tunnels. New Delhi has successfully completed this. This is a cross section. You can see that there is from the center to center 21 meter of the two platform tunnels and the connection tunnel in between these tunnels. Pacific Station for the Seattle Metro, the very special aspect of the Seattle Metro is that it is very deep because the tunnel has to go under the fjord. Seattle has the city of Seattle is on the Pacific coast. There are fjords similar to Norway, and to go from the center of the town, this line was to connect with the university. It has been necessary to go very deep under the fjord, so the station is more than 300 feet, more than 100 meter deep, and the access to such a deep station only can go through shafts. You could not have access through inclined shafts. It has been necessary to do it with vertical shafts. So this is another Metro Budapest, the so-called Gellert station, near to the river Danube in Budapest. It is, instead of consisting of two station tunnels, there is a three multiple drift station here, with the platform tunnels on the outside and the passenger distribution tunnel in between. All of this is possible only with the conventional mining method. That's the binocular type Gellert station, again in a cross section. In a cross section here with cross passages between the platform tunnels, and here we have a longitudinal section. So what are station design issues? Beyond economy, the designer should consider the following major aspects. First of all, the size and the shape and the number of drifts and the number of shifting of stresses in the underground. It is always an advantage if it is a symmetrical structure. Computation, everything has to be computed before we go into construction, in particular where we have to look into stress-strain relations. Then we have to look into the necessities of the geotechnical aspects, necessity in regard to pre-support, mechanical pre-support. We have a number of tools for this pre-support nowadays, in particular also to the question of soil improvement, which for Bangkok certainly is a very important issue. There are construction issues for multiple drift stations. Design and construction method shall satisfy all project conditions defined by the geology, geometry, and by the environment. These are given conditions. Construction activity on surface will be limited to a minimum, and multiple drift station is limited to construction access shafts to be covered. So we cannot have a multiple drift station. Okay, we cannot have a multiple drift station without the access, and the access has to be a cut and cover structure part. So there are structural issues like shotcrete lining. It has to take full loading in construction. This is a conservative assumption nowadays. Shotcrete quality has been significantly improved, and more projects are getting shotcrete as a final structure lining. The final lining is then designed to take full loading where shotcrete properties are converted into soil properties. Again, to convert it into soil properties is a conservative approach. And it has to be based on the superposition of load cases. We have to make the individual load case investigation, but then finally we have to make the superposition. Some numerical analysis for the metro of Vienna. I have to go a little bit faster. Then we have for the metro Budapest double tube mine stations. I indicated that before already. So this is the construction sequence for a multiple drift, for a triple multiple drift construction sequence. That's how the interface between the cut and cover and the TBM tunnel and the NATM tunnel would look like. You can see here that this is the TBM tunnel, this is the NATM station excavation profile, and here we have the cut and cover access to the station. In conventional station design, environmental advantages are evident near, in particular near or underneath sensitive structures. Economic advantages against open cut techniques are inevitable when considering life cycle cost. We have another couple of cities right now which start to implement metros in different parts of the world. For instance, in Chile, in Santiago, and in Lima, in Peru. So these life cycle costs nowadays are a standard criteria for the decision what construction should be done. And risk has to be controlled. There is always a risk in underground structure. However, there are no new risks. These risks, which are all known and can be mitigated, can be assessed and can be controlled through risk mitigation. Climate change, you know, if we look to the melting ice on the poles, we know that we are 5 minutes before midnight with our measures. We have to take measures in order to mitigate the risk which comes from climate change, melting ice, increase of the seawater level. So here you can see different forecasts for, here we have here we have 2000, here we have 2050, here we have 2100, 2300, and in any case, whether we we look into cooling or stable or warming conditions, we can see that the temperature curve increases. So climate change is for sure out of question. It's going to happen. The future of our cities, they will increasingly become dominating our planet. Today already more people live in cities than in rural areas, and by 2050 the world cities will absorb 3 billion, additional 3 billion people. So 2/3 up to 70% of the population of our planet will live in urban areas. Global population nowadays is 7.3 billion, not 7.1. The population increase per year is 80 million. We will have 10 plus billion people in 2050, so we have to look into social and political aspect at present and in the future, which all indicate there is more need for underground space. An example from Korea, where originally the city and the river Jeoncheon has been covered with concrete bridges. Now this river is again given back to the people in Seoul as an example. Another example is the so-called Boston Central Artery. Here you can see the tunnel. Before all of this traffic of I-95, Interstate 95 in Boston was running through the center of the city. Now it's underground and the center of the city is very green and livable. Urban infrastructures are for different purposes, for water supply disposal, transportation, parking, shopping malls, storage, and water lines. So we have early global metros since 1863. London claims to be the first. Istanbul at the same time say no, not London. It has been Istanbul in Turkey, then followed by Budapest, Paris, New York, Berlin, Hamburg. Nowadays we have more than 100 cities. Europe transportation tunnels, we have in Austria, I'm counting from Austria, close to 600 kilometers, Germany 1,400, and in all Europe we have 16,000 kilometers of transportation tunnels only. The largest TBM right now is on the so-called Alaska Highway in Seattle. It's a 15.7 meter diameter tunnel boring machine, at this moment not working. People are facing geotechnical problems. This is a smaller tunnel with so-called controlled kinematics in order to put the segments together to form a ring. It is much easier to follow the principle of Lego. If you know your children, they like to play with Lego, they put the stones together. The same principle you can use also for the segments in our tunnels. This is the startup situation of a TBM for that same project. Now we have innovations in conventional tunneling. You may look into your slides. I'm thinking I'm running out of time. There are the connection control. If we have multiple drift, we have to particularly look into the connection of the multiple drift areas with the final structure. We have conventional tunneling phase and in situ lining, of course, shotcrete lattice girders. We have sometimes very squeezing ground conditions. Very squeezing ground conditions comes because we have forces, the loads, geostatic loads, which are deforming, which are settling the roof here and moving the sidewalls outside. Flood can be controlled with flood tunnels. Just to let you know the real cost of the damage in 2011, November 2011 here in Thailand, has been paid, 1/3 has been paid by the insurance companies, and it's the amazing amount of $30 billion US. This is only 1/3. So the real damage has been $100 billion US from one flood event in 2011. And we can control flood with tunnels. This is the flood caused by the Sandy storm, very well known, and it was predicted to be over after 6 or 7 days by the mayor, and then actually it has been more than 3 weeks that the New York subway has been under the influence of floods. All of the coastal areas are at risk, in particular with climate change and melting ice falls. This is a funny picture you can see here. This is the flood warning center, the early warning center Of course, we have the state-of-the-art electronic equipment with capacity for most accurate predictions, dependent completely on the totally unreliable weather. So this is the fact that we have to use more tunnels in order to mitigate this problem. This is the example which works in Boston, because I have been working on that project in order to control a flood which comes for a 15 million population of the greater Boston area. And this Boston outfall tunnel is using 400 feet of shaft and then draining out the water into the diffuser heads in the harbor of the tunnel. Here you can see a block picture, and it perfectly works. So the question was, this is the idea which I developed for Thailand here, for the greater Bangkok area, flood relief tunnel. The motto has been, how can we clean the dirtiest harbor in the world, which Boston has been actually, and I have seen both before this tunnel has been implemented and after, and now it's a very, very clean project. That's another idea of the same model. So we can go with use the underground for power plants. I have no more time to explain some more, but in particular for nuclear power plants, it is obvious that at this moment there is a preoccupation of mind by the planners of nuclear power plants that they want to follow the principle of Fukushima, which was a terrible accident because of the tsunami and the high waves, and we all have known that because it has been for weeks daily or for months daily in the media. We should go with our power plants underground, because the underground will protect. So there is Fukushima, there is risk and structure comparison. Of course, the risk is much better controlled underground than above ground, because rock overburden has a better protection, gives a better protection than concrete, even if the concrete is very heavy. Now, in the hydroelectric power schemes, we go underground. There are many examples of big underground caverns in the world. I think more than 100 underground power plants with generator halls and turbine halls. This is an example from New Zealand, the Manapuri Powerhouse, which is underground. There are ascending tunnel projects where we use tunnel technology of up to almost 20-meter diameter in St. Petersburg in Russia. The project has not yet started, but the machine has been designed and completely prepared. This is this double-deck tunnel, almost 20-meter diameter. Transcontinental mass transport between Siberia and between Alaska is a project. It's an engineering dream, but I think it's going very close to become reality, maybe in 10, maybe in 20 years. Another idea is the tunnel between Java and Sumatra in Indonesia. It's a 35 or 33 kilometer long tunnel. It's also in the phase of study like the Gibraltar tunnel. Bangkok is going to extend its metro system and to spend approximately 800 billion Thai baht, 800 billion Thai baht for the next 10 years. Like one of the examples of the Blue Line extension, we heard about the Blue Line extension and the Samdam Chai station in the morning lectures. Singapore also is going to spend 20 billion US dollars, not Singapore, no, maybe Singapore, 20 billion Singapore dollars in the next couple of years. So Singapore will also have a mass transport system in the range of 450 kilometers. Freight could be also transported underground. There is a logistic benefit to it, there is an economic benefit to it. There's an environmental benefit to that. And finally, the cost benefit of urban tunneling. I'm just summarizing some pictures. There are cost comparison between mainly German cities in this slide, and a split of average cost, which is about 74,000 US dollars on nowadays dollar value, including design, track work, and electrical mechanical works. We have a summary of German subways, and you can see that it's quite different between 23,000 US dollars per meter of tunnel, and the most expensive one is 94,000. That's a more detailed, and please look into the handout for the comparison of this cost and the split of the average cost. For the Munich subway, it's amazing, much lower than Singapore, with 45,000 US dollar per meter, including different construction methods. Very expensive, unfortunately, the Vienna subway, and I told you the Vienna subway came about 15 years after, or started about 15 years after the start of metro construction in Germany. So the experience has been quite fresh to mate, and finally it was more expensive. Split of average cost at close to 100,000 US dollar per meter. But if we look into only conventional tunneling methods in Vienna, we come up with 125,000, not taking into consideration life cycle cost. So what is the future of urban tunneling? We have to make a partnership between engineering and geotechnology for underground structures. They show the importance of independent consultants. We should not squeeze the consultants now. I'm biased a little bit. It should be a fair sharing of risk. This is important. The risk, which is always there, should be fair shared, and there are guidelines for that. So the party who is most capable to manage the risk should also be allocated with the risk. The contractors should have a commercial benefit, and the owners should be satisfied in the result of quality and performance. So, thank you very much. There's one in between, maybe. Yeah. Okay. Thank you very much for your attention, and please don't hesitate to ask questions. I think we arranged for the questions afterwards.
Yes. Thank you very much, Dr. Wagner. สำหรับคำถามนะครับเดี๋ยวจะตอนช่วงท้ายเซสชันจะถ้ามีเวลาเหลือเราจะเปิดช่วงนั้นให้ถามตอบกันนะครับ On the behalf of our organizing committee, I would like to express our sincere gratitude and appreciation to you for the knowledge given us on this conference. Next, I would like to invite Dr. Thanu to give a token of our gratitude to Dr. Wagner, please.